This podcast was produced from a webinar. For a more interactive experience with visuals, visit advancedmanufacturing.org/webinars.
So what we're going to do today is we're going to talk a little bit about, kind of the process of choosing to automate and going through an ROI calculation, how you should really kind of evaluate what you're doing when you're getting started with automation. So we'll talk about some recaps of some stuff Epson's done in the past that's out there for your viewing. Talk about building automation, then meeting spec and how ROI calculates in that. Then kind of coming up with the new concept of rather than meeting spec of solving problems. And then try to give you guys an example of how this really works and bring it all together at the end. So again, you can go out there and we've done, a series of other webinars on topics related to automation, starting with our Epson Automation 101, where we kind of got through kind of a 5-step process of starting with automation, deciding that you want to automate. And as what we've done over the course of the last couple of years is we've kind of expanded on these ideas. We had a presentation called Automation 201 where we were talking about identifying your requirements, and then we kind of clarified what those requirements really meant. Then we figured out how to kind of define your process and improve your process for automation. And then today we're going to take another step backwards and look at what's driving the automation decision and really kind of give you an idea of how to go about that and really decide what the best path forward for you is. That I always like to start kind of as a history lesson in automation of thinking about how we got where we are today. And if you look back in the 60s and 70s, what traditional manufacturing looked like, it was, a lot of people on a conveyor belt, a lot of people working at assembly tables, putting things together all by hand. And as automation started to get big in the 70s and 80s, robots started becoming more and more accessible. There was this idea of the dark factory, the idea that one day your entire manufacturing process was going to be done by robots, and that you were going to, at the end of the day, turn the lights off. The robots were going to run all through the night, and in the morning you're going to turn the lights back on, and all your products, all ready to go, ready to ship to your customers. But in reality, that never really happened. And what you end up having is what most people would consider as robotic processes, and then what most people would consider manual processes. And they're separate, right? There are specific things that the robots do. There are specific things the people do, and there's not a lot of crossover there. So rather than this idealized automation where robots were doing everything, you really had these kind of silos where robots were doing certain things and people were doing other things. And the question is why? Why did it end up like this? And the answer is because when we first got into robots, we were like, oh yeah, robots can do everything people do. But that's not really the reality. In reality, robot applications that have historically been the most successful are executing tasks where people struggle. And, you can break this down into 3 specific areas historically. One is speed. Robots can go a lot faster than people can, right? Robots don't get tired, so they're going to go just as fast at the beginning of the day as they are at the end of the day. So when it comes to assembly, robots can go a lot faster for a lot longer than people can. They're also much more precise, right? They can lay down parts in a much higher density than people can. Again, they don't get tired. They're very repeatable, so they're able to put down parts very, very close together and do it the same every single time. And so that precision is really great for robotic applications. And, payload, they're really good at carrying heavy stuff, right? So if you see car parts or dangerous materials, robots can pick those up and move them around without danger to themselves because, obviously they're not people. They don't get hurt the same way people do. So, in terms of going super fast, being really precise, or carrying heavy payloads, that's where robots, really, really do well. Where they struggle is when there's any type of decision-making that needs to be done, what we consider ambiguity. And what that means is when you think about a process, whether or not a robot is doing it or a person's doing it, there's always this kind of accept and reject area. You can think about it, you cook a piece of toast in the morning and you look at it and you're like, well, is that good or is it burnt? right? You look at it and you make a judgment call about whether or not that's a good piece of toast or where's a bad piece of toast. If you wanted a robot to do that, you would have to put a hard line there. So in this judgment area, if you're a person, it's like, okay, I'm going to look at my piece of toast and I can decide somewhere in here is good, and I'm going to make a judgment call. And people are really, really good at doing this just by using their own preferences, their own experiences. We make tons of decisions like this every single day, all the time, without really thinking about it. With a robot, you have to put a hard line where everything above this is acceptable and everything below this is unacceptable. And there's no judgment, right? That line, that metric that you use to measure it is the total line for everything above this is accepted and everything's below that is rejected. And everything between in that judgment zone before that, because what you usually do is you set that acceptable line at the top of the judgment zone, so you make sure you don't get any bad parts in there. That's all potential waste, and you have to decide what you do with that. Do you just throw it away? Do you rework it? Do you just eat the cost? Do you just send it out? Maybe you just send it out. Maybe you send that line at the bottom and you send all the possible things there. And then you have the opposite problem of maybe customers are upset because they're getting kind of inferior products. So, where these people make decisions all the time and can make them very well, the robot, it's much, much harder. So you got to set this hard line in the judgment zone. And because of this, right, you get processes that are robotic processes where this judgment zone's very, very clear cut. It's very clear what's good and what's bad. And we have one of those three problems that we established in the last slide, where with people, you can give them ones where you need more judgment. It's more kind of as much art as science. They're using their experience and making a bunch of little decisions to make things right. And those end up being the manual processes. But yet, in spite of the fact that we understand this now, we understand that you can't just put a robot and replace a person with it, because you got to really understand what the person does. We still design robot cells kind of the same way. A lot of times the way people will develop a robot cell is they'll follow a person around and they'll look at what the person does, and then that will become what they want the robot to do, right? We want the robot to do everything that this person does. So you evaluate the process and then you try to replace the labor. And even though we know that this hasn't worked because of what we talked about it, this is still a lot of the ways we look to design robotics. And within it, it leads into something that we like to call an ROI calculation execution. And that's kind of goes through this steps of you first evaluate your process. Then you design your work cell, you design your robot work cell to do all the different things you saw that person do. And then you calculate the ROI. And the ROI becomes a pretty simple equation because you know how much the systems cost and you know how much the labor was costing you to do the same thing, and that gives you an ROI. And then you either accept the proposal or you say, look, the system's too costly because you can't really do anything with the bottom half of the equation. The bottom half of the equation's fixed. So the only way you can get is you cost reduce. And cost reducing with the robotic work cell is difficult, right? Because you laid out an application, you tried to figure out what you need to do to get the job done, and you design the work cell. So, again, bottom of the equation's fixed, but the top of the equation's kind of fixed too, because that's what you need to do to get the job done. So in order to cost reduce, you start reducing the spec. And what does that mean? And for me, it comes down to kind of the question of how do you fit a square peg in a round hole, right? That's the situation you have. You've got a square peg and it's not what you need from the ROI point of view. So you need to fit it in the round hole. So how do you do it? Well, the easiest way is you make the hole bigger. And that's not necessarily the best solution. And that's what reducing the spec really is. Because in order to reduce the work cell cost in this way, you end up doing a few different things. You may reduce the speed needed. You may get a less performance-based robot that's cheaper and say, well, we're going to compromise on the speed of the robot and make something cheaper so we can get the ROI need. You might increase the tolerances. You might literally make the holes bigger. So again, maybe you can use a cheaper robot. Maybe you can go a little bit faster. Maybe you can, squeeze a little bit more out of this work cell design, but by making the tolerance less tight. You could decrease the functionality. You could start saying, well, we don't need this, get rid of that. We don't need this, get rid of that. Just pulling pieces out of the work cell to make it cheaper. Or you might decrease testing, which kind of goes back to that judgment call, right? You may lower that line to a lower threshold to get more product out, and it may be of a lesser quality. So in all these things, as you start to make these decisions on how to save money on the work cell, you're really compromising the integrity of the work cell and really the performance you're getting out of it. And so at the end of the day, this isn't really the best solution. And so how do you get out of this? And the important part of this, the way to think about this in a way that avoids this is, rather than focusing on cost and then spec reduction, is to go back to your initial process and ask the question, why are you automating? And that's actually a very interesting question, because one thing I've learned in my 20 years of robotics is no one turns to automation if everything's going great. Well, when they have a production capacity issue, they'll just add more labor. And adding more labor is usually a pretty straightforward way to do it. And, if you just got more orders than you can handle and you're just going to add more labor, if you don't have a fundamental problem with your process, it works out great. But the people who turn to automation are trying to actually fix a fundamental problem with the way their process is going now. And that gets us back to speed, precision, and payload, right? The three things that robots do well. And fundamentally, most of the time, people are starting to look at automation. They've got one of three problems they're trying to solve. And this is actually why the specs of a robot are super, super important. If you ever have talked to a robot guy, try to buy a robot, this is like ask you, how fast do you need to go? How precise do you need to be? What's the payload you need to pick up? And it's because there are these three fundamental problems they're trying to solve. The first one being throughput. Obviously, people can only go so fast. And if you need people to go faster, obviously you can add. But if the process is just kind of beyond what they're capable of, adding more people just snowballs on you, because you have to add so many people and they still can't keep up. And if they need to be going super fast their entire day, obviously they're not going to be going as fast at the end of the day as they are at the beginning. So you still lose some throughput because of that. Precision is really a quality issue. When you're trying to put down pieces and get it right every single time, again, as people get tired, they get sloppier, they make more mistakes, your quality is going to suffer. And payload's really a safety issue. As people, again, pick up heavy payloads, carry them around all day, they get tired, they're more likely to drop stuff, they're more likely to not be paying attention, they're more likely to get hurt. So each one of these fundamental robot strengths is a fundamental person weakness, right? And so this is the kind of solutions that people are trying to solve when they turn to automation, right? I always like to think about it as no one turns to automation when everything's going great. When they turn to automation, we want to figure out exactly what the problem they're having that can't just be solved by adding more bodies and adding more people to that assembly line. And if you look at the three industries where automation has historically been the most successful, which are automotive, electronics, and life science, each one of them had a problem with throughput, quality, and safety that robotics solved for them. With the automotive business, right, it's car parts are heavy, right? They're really super heavy. If you think about welding in a car door into it, you look at the old pictures and they're like two guys holding a car door while a third one, welded it in place. Well, now you see a single robot grabbing on that door and another robot welding it into place. And again, they're not going to get tired. They're not going to get hurt. They're going to be able to hold that in the same place every single time without any damage to themselves. So really you get higher throughput because you get continuous work. You get higher quality because it's a repeatable process. You don't have guys getting tired and maybe not holding that door in that perfect place at the end of the day. And you're getting rid of that repetitive work strain from that, really hard labor. For electronics, it's been the miniaturization of the chip industry, right? As you get through every single generation of your technology, it's getting smaller and smaller, right? TVs getting thinner, phones getting smaller, more and more processing power in the same chip. They've got to put components closer and closer together on these chips, which got harder and harder for people to do. So as they got to higher and higher density, having the higher precision and the higher speeds allowed for better throughput, it allowed for better quality. And, from the safety point of view, you had people in those, full bunny suits that are hot and hard to manage and stuff like that. They're doing smaller and smaller things with repetitive stress. You're putting people in a safer environment. Life sciences has a lot in common with electronics when you get into the miniaturization of medical technology, the wearables, the consumables, all that kind of stuff as well. But there's other factor as well. We saw with COVID testing, needed to take a COVID test right there in order to enter. A lot of times they would have a person just sitting there. Now you're exposing that person to COVID, but they're also just having to wait around and wait for people to show up. And the times when they're not, they're just waiting. Robots are really good at waiting and then responding exactly when you need them to. You get more traceability because the robot's going to follow the same process every single time, and seeing that dangerous exposure to potentially dangerous chemicals or infectious disease that a robot's obviously not going to have a problem with. So as you look at each one of these concepts and say, okay, there's throughput, there's quality and safety, there's more than just that labor cost savings we were referring to early in the presentation. That labor cost savings is always part of it, right? That is always a part of automation. You're trying to do more with less, being efficient, having more efficiencies. That's a goal of every business. Right. So it's not like that's not there, and it's not like that's important. That obviously is one of the big gains you always get with automation. But there's so much more beyond that. There's not only just the labor cost savings, but there's the potential to actually build more. Now, whether that's just in raw speed because the robots go very well, or it's because there's less scrap or there's more precision in it, you're able to get, a higher yield because the robot has that high precision and has those high speeds and doesn't get tired at the end of the day. You may just get more stuff out. You could also get better stuff out. We talked about the miniaturizations of chips. Chip density never could have gotten to the place where it was now doing it by hand. You would need automation to get to those levels of chip density as we get, smaller and smaller wearables, for medical devices, all the stuff that we're starting to, track on our body. That kind of stuff wouldn't have been possible without robotic automation. And increased traceability gives you the ability, again, because the process is done every single time. It's done by computer. You have the ability to save all that data to a disk and reference it later. That allows you to track and guarantee that the process is the same, have that traceability to show it was the same. And if there was an issue, go back to those records and try to figure out what went wrong so you can make improvements and maybe recall only exactly the ones that went through the process that had the issues. And then safety, right? Fewer accidents, less people getting tired, less people put in hard physical strain, and then, improve worker happiness because, people don't like doing the same mindless tasks all the time. They like to be engaged. They like to be using their brain to make judgment calls. And that's what we're doing here, right? We're taking them away from the mindless drudgery that the robot's really good at them and putting those people in situations where they're using their judgment to make decisions and hopefully making the entire process more productive. So when you take these concepts and you look at kind of an income statement, historically, when you do that ROI calculation, you're really only looking at that middle labor cost savings, right? Okay, I'm going to save cost. This is how much it's going to cost me to buy the work cell. How quickly do I pay that back? But that's really only looking at one aspect of the gains you could be making in automation by actually solving your problems and not just trying to replace labor, right? So again, increase product capacity, increase product development, that's going to lead to more sales, right? You're going to have more of a better product. And right, again, people are turning automation because they've got bottlenecks, because they've got issues, they got supply chain issues. If you're not at the point where these kind of things benefit for you, you're not really at the point where you need automation yet. As we talked about the precision, we talked about the ability to have more repeatability. That reduces scrap, that reduces your cost of goods sold, right? Cost of goods sold usually has a scrap component in it. The labor cost savings we talked about, fewer accidents, improved worker happiness, the ability to carry less insurance because you're not putting workers in risk. You don't have as many accidents, you don't have to pay that out. And then that warranty liability from increased traceability, because again, you know things are being done correctly. You don't have to worry about it as much. And if there is a problem, you can just recall exactly the ones that went through the process. So the point of all that is to kind of come back to this of rather than getting into this ROI, labor reduction, cost reducing cycle, the better thing to do is to start up here in evaluating a process and determine what problems you're really trying to solve. And so as you evaluate the process, you say, okay, what's my fundamental problem? And then you kind of go back here, and rather than trying to replace the labor, what you want is a new process, which is a robotic process. And what does a robotic process look like? Well, it's not just robots. It's actually robots and people together. So the robots are doing the high speed, the high precision, not a lot of thought, potentially dangerous work that people struggle with. And the people are making the judgment calls, right? As there are things that require more judgment, are kind of more art than science, require some human ingenuity and human thought to it. That's where you put the people, right? So rather than taking the process and just trying to get the person out of there and drop the robot in, you look at the person and say, okay, how can I make this guy's job better by using a robot to take some of the stressful burden off this person's job and using them more efficiently to get more throughput and make better decisions throughout the process. All right, so how do you actually do this? In our last 301 presentation, we went through an example of how to kind of break down a process and turn it into a robotic process. So I would highly recommend you go seek that out. If you have more questions about that, you can contact Epson if you have more questions about that. But what we did is we made this example of a bearing on a shaft. And a bearing on a shaft is a pretty simple mechanical process that, usually you put some sort of spacer or some sort of clamp on the shaft in order to set the bearing at the right space. It might be a press-on bearing. You might be adding some adhesive. You do that, then you press on the bearing, you let it dry, and you're done, right? And that, if you were explaining that to a worker, you'd be basically like, okay, set the height by doing this, press the bearing on, done. But when you're explaining it to a robot or trying to design this robot process, it's much more complicated because, again, that person is making a bunch of judgment calls that the robot doesn't really think about, that the person doesn't think about, but the robot does. Like singulating the shafts, right? A robot, you can just tell a person to go grab a shaft out of a bag of shafts. You can't tell a robot to that. You got to find some way to singulate those shafts so the robot can do it. Same thing with those spacers. You got to tell the robot to place the spacer on the shaft, and you got to then tell them to maybe put the adhesive on, singulate the bearings, put the bearings on, test that and make sure it's okay, and then place the part in some sort of fixture so it's ready for the next step. So this is what it would look like if you just took that whole process, took the person out of it, made a robot do it, right? It becomes much more complicated because of those things. You get rid of all those little judgments the people make throughout the process. So what's something that's simple for a person to do becomes a complex process for a robot. So now what we want to do is look at this process, look at what kind of fundamental problems you might have, and look at how you automate this with people and robots in mind. So let's talk first about throughput. It's like, okay, you're just not producing enough product. Well, normally that's a assembly limitation. It's some reason why just throwing more bodies at the assembly stage isn't increasing your throughput as much as you want. And so if your bottleneck is just producing a product, this is your main assembly stage. This is a great place to use robotics, because this is why robotics were invented in the first place, right? To do this main assembly step at extremely high speeds in a repeatable way that is not creating mistakes. So if your fundamental problem is throughput, you want to break down what your main assembly stage is and see if you can get a robot to do that. And as you kind of go through that, you can look and see, well, are there other things that are managing my throughput as well? Maybe the assemblers are doing really, really well and consuming all the material that they have, but there's a problem downstream and they're not getting the material as fast as they need it. Well, then that's kind of a prep problem, right? Can you automate your prep? Is there a way to put automation in that makes it so it's easier to prep your parts and get them to that assembly stage faster? There are tons and tons of automated tools to do individual prep. And the question is, again, right, why isn't this prep stage happening faster? If it's because, well, we're making a lot of decisions and there's a lot of decisions have to go to where these parts need to be. If you can set hard and fast guidelines on exactly what needs to be done, well, then you can use automation. But if people are using a bunch of judgment calls, that's not a great place for automation. And you just need to find either a way to take those hard judgment calls and make them easy judgment calls to use automation, or you're just going to need to scale up with more people. If it comes to a quality problem, like the bearings are not spinning, well, then that's potentially a problem with testing. It could be a problem with assembling. It could be a problem with the prep stage, right? There's all kinds of different problems that could be happening. Drill down and figure out why this is happening and where we can add automation to help. Maybe you're letting too many of these bearings get into the process that were bad to begin with. And maybe you're doing this because you don't have the time or manpower to test those bearings. Well, you can automate that. You could put in automated test systems so that these people can test faster, as long as there's a hard and set rule of what's good and what's bad. Or maybe you have an assembly problem where there's some problem with the assembly. People are trying to go too fast and make mistakes. People are trying to figure out certain inequities in the parts. Maybe you need to check other parts in order to make sure that the assemblers can go as fast as they need to go. So maybe there's an automated test stage you can add in at the prep. Or maybe it's something that you need to add automation into the assembly, and those can also test so you can speed up that process, right? Again, figure out where the problem with the bearings occurring, and then you can figure out where the testing does the most good and if automated testing is right for you. If the bearings are not in the proper position, right, is this a prep problem because you're not properly prepping your bearing with these spacers in the right way, or are you just not assembling it right? And is there some testing that should be in here that's going to solve that problem, right? Is this really a speed problem? Is this a repeatability problem? Or is this the testing problem? Figure out where you can put the test stage in to be the most effective. Figure out where the problems are occurring and figuring out if those problems are because of precision, repeatability with hard and fast guidelines that robots can do. Then automation is a great way to do it. Again, if the problem is you got to make too many decisions, a robot's not going to solve that problem. If you're getting customer complaints, you ship these things out and all of a sudden the customer's complaining about not getting reliable material. Again, getting automation into the key steps where those are happening gives you not only the better performance of a robot in terms of speed, repeatability, but it also gives you traceability. It's hard to get people to always write down everything they did. And, you kind of get into a mindset of, well, I do this, and then I check off all these boxes without you kind of lose scope of what all these boxes you're checking off is. This is just what I do once I know I'm done with my job. The robot's tracking everything that it does. It can record it. It can store that for your later use. If you've got customer complaints, you can maybe get those serial numbers, track it back to the process, and really look at the data and see if anything went wrong, or see if there's differences between batches to batches. Again, it's going to allow you to help isolate those problems when they're out in the field much, much better with the traceability that a robot provides you if you're backing up and saving all that data. And then, again, the safety thing's very straightforward. People are around toxic chemicals in prep or bonding. They're, again, having repetitive stress pains. They're working around dangerous environments. We had a application once where we had people working around a really hot furnace that was, causing them a lot of discomfort. Any of those kind of things where people are in danger or struggling, a robot's a great way to get people out of those environments and into safer environments where they can be happier and safer. So how do you do this in practice? And again, you kind of look at the old way of doing it, and the spec questions are still super important. You still need to define the components of what your process is. You start off and say, how many parts do you need to process? What's the working area? How big is it? How much do the part weighs? And those questions are still super important. You're never going to get away from those. That's a key component of automation. But what this presentation is really about is trying to go a step beyond that. Of asking all those questions and then fundamentally getting back to the question of what problem are we really trying to solve, right? Why are we going to automation? Why is scaling up with people just not going to work? How do we solve this problem? Because then once you get down to that problem, you can really target in what part of the process you're trying to figure out. And automating that is much more straightforward. And a lot of times it's lower cost as well, because you're not trying to take on this big, huge, gigantic process that the person does, but really just aspects of the process where you can show the most improvement. So, it's lower cost and it really gives you a lot more bang for your buck. Then, as you look at the areas for improvement, going beyond what we're doing now, and is there a way to do it better? Like we talked about, where are you testing? How are you testing? Is that really the best way to have the highest throughput and the highest quality, depending on where we are? Because, once you test something and you put it in the robotic process, it shouldn't change. So there shouldn't be a lot of damage to it. So maybe testing earlier is better, and you don't have to test late. Maybe that streamlines your process better. And then what comes next? Because, as oftentimes happens with robotics, you get your first work cell developed and it works well. You start looking for the next challenge to tackle and the next process to decide on. If you're kind of thinking about that when you do your first work cell, you can develop in a way that's going to be scalable to the rest of your process, and a way to really hone in on the value you can provide your company. So our summary is to focus on process, not spec. Don't really look at what someone is doing and try to replace them. Try to focus on, what the problem is and what you're trying to improve. And then look at whether or not that problem is an aspect of throughput, quality, or safety. Because if it is, those are great robot tools. Great tools. Robot has great tools for solving those problems. If the problem is, you have to make too many decisions, there's too much variability that you have to account for, there are tools that robots have to deal with kind of that stuff. But again, if you can't set those hard and fast lines, the robotic solution's not always the best bet. And talk to experts, because a lot of times, especially if you're getting started in robotics, or even if you have some experience in robotics, the robotics world is big. We cover a lot of different industries, and because of it, there's a lot of tools that are developing for other industries that you may not be aware of, that we can point you in the right direction and help you decide, what's the best tool for the job. And ultimately, at a company like Epson, we like to be, partners and help you through your automation journey. So a lot of times when you talk to us, we'll come back and say, hey, look, this isn't the greatest robotic application for, the reasons we showed you. Did you ever think about this or this or this? And sometimes, we get to a solution that's not a robot, but hopefully we can become a resource for you now into the future as you go through your automation journey. So at this point, that's the end of the presentation. So I'll turn it over to the host for the Q&A section.
Thank you, James, for such an insightful presentation. It looks like we did receive some questions from our audience. So a quick reminder to our attendees to get your questions in while we still have our expert here on hand. And so our first question looks like if you have costs, if you have to reduce costs, what is the best way to do so?
Yeah, so we have to be realistic as we get that cycle of cost reducing and ROI. It is important. We can't ignore that completely. And sometimes you just don't have the budget in to really get the system you need. But that's why a big part of this presentation is trying to reduce the scope. So rather than reducing the capabilities of the work cell, or basically getting something that isn't really what you want, really target in on the core problem you're trying to solve. Reduce the scope of the overall project to solving that core product, and then make sure that you have a system that actually solves that problem. And if you just can't afford that system, you have to just make that decision about whether or not those compromises actually solve those problems. Because sometimes you can't say, oh, look, I want to make 30, in this amount of time, but I can get away with 25. That's fine. So a lot of what we talk about in a lot of the other presentations Epson does is you do need to think about trade-offs. And there are trade-offs with every single automated system. So you just have to identify what trade-off you're the most okay with and design a system that gets what you want as much as you possibly can and sacrifices what you're okay with sacrificing. So think about those trade-offs, talk to experts. We can help you do that.
Great, thank you. And if you have multiple problems you're trying to solve, how do you prioritize?
I think the key is, again, to look at where you get the most bang for your buck. Look at what's the most fundamental problem, right? What's the most fundamental bottleneck? And that kind of goes to what comes next. It may be what's the simplest problem to solve. Maybe there's something that other people have done a lot and this is going to work. Tackling the simplest part of it is a lot of times the best way to get the bang for your buck. It's going to be the lowest cost solution to that. And it's going to be the most effective because, it's the most thought out. So again, kind of look at where you can get the most bang for your buck. And at all, I'm always for defaulting to easy. Default to easy and get done, prove out that this is going to work. And then you usually get a lot more buy-in from people as you have something that actually works.
Great, thank you. We have another question here. How do you calculate ROI using the profit model you described?
That's hard because, there's not a lot of different ways to project stuff like worker happiness. But what I would do is you kind of look at your income sheet and you kind of sit there and say, okay, if we have this robotic system, we're going to get, a better product. How much it's kind of it turns into a product development kind of exercise. If you're thinking about, developing a new product, you always have to look at, well, how much more money am I going to make? How many more of these are going to sell? What does it do the rest of the business? That's kind of what you want to do for the ROI example in this is go through that process of all the different improvements that this system is potentially going to give you. try to quantify where you're at now versus where you're going to be if this all goes, well, moderately well, and not well at all. Kind of decide which one of those scenarios is the best and use those three kind of tiers to figure out, what kind of payback you need for your system costs. But you treat it more as a kind of a business development project rather than an engineering one.
Great. We have another question just came in here. How is artificial intelligence affecting the cost structure?
So artificial intelligence is interesting. The main place you've seen artificial intelligence adopted in kind of the traditional industrial robotics world is in path planning. But at the same time, a lot of times the path planning is a lot of that's solved. A lot of times, if you're working with someone who's done a lot of robotic app implementations, the AI doesn't actually make that much of an improvement. You have seen some AI developments in the teaching aspects of robots and in the maybe how to adapt to more different situations. Maybe you can get into a little bit more of that that we talked about, laying out that hard line. Now, what AI does is it doesn't really give you a more blurred line like a person does. What AI does is it actually just kind of continually moves that line and maybe refines that line to a little bit better place than you had set kind of arbitrarily or just with your own knowledge. So you potentially can save a little bit on the system integration time, shortening that time, potentially getting, just some labor cost savings as well. You can also potentially get some scrap reduction in that judgment call area, improvement in line. But in general, we haven't seen a big push to use AI successfully in industrial robots. You've seen it a lot more in the kind of AMR world, if you're familiar with the autonomous mobile robots, which Epson doesn't deal with. It's kind of a different industry. But in terms of the greater path planning, like navigating around a hospital or a 3PL facility, a logistics facility, used there. Because in that kind of world, the path pattern is not specific; it's variable. So that's where you've seen really big gains in AI and robotics, and kind of the traditional industrial world where you're looking to optimize a process the same way every single time. The AI gains haven't been as great.
Terrific, thanks. And it's looking like that was our last question, unless we have any last attendees that want to get a question in. All right, well, in that case, I want to thank James again from Epson for joining us today and sharing such a great informative presentation on this very timely topic. I also want to thank our attendees for your participation and great questions. We hope you found the content valuable and you'll join us again soon. Until then, remember that SME and SME Media are here to help you stay up to date on all things manufacturing. You can find links to podcasts, webinars, publications, and news by visiting us at advancedmanufacturing.org. Oh, and I do see one last question here, just for James. Is there a contact email for you that someone could reach out to you at?
Yeah, it's james.shimano@ea.epson.com. There's also, if you go to the Epson website, there's a tab for robots. You can get into, kind of our general line and get to us in general through that as well.
Wonderful, thank you. And that'll also be available with the recorded webinar that'll be made available later today. So thank you again, James, and to our attendees, thank you so much for joining us.